Megan's really hoping I don't go another 2 meters. I won't. And just that amount of information is enough for it to have a pretty good belief about where it is, okay? There's still some probability that it's over here, because if that previous reading was just wrong and the current reading was right, then I might be there. Same over here. If the current reading was right, but the previous reading was wrong. No, the other way around. Anyway, the idea is that it's weighting these different probabilities, okay? And you could, do it again. So you resample and you move. And you see here, we have the resample density where most of its belief is in the right place, and there's some densities there, and that's it. And that's the way a particle filter works, okay? Algorithmically, it's pretty straightforward to do this, all right? We start off at any point in time, we have a set of particles at the last time step, and each particle has a state, like its position, and a weight. And we're also going to be given a new action, like take a step to the right 2 meters, and we're going to take a new measurement. And then here's how the particle filter runs. We start off with a new set of particles empty and a normalization constant of 0. Makes sense. And then we just do the following n times, where n is the number of particles that we need, all right? So the first thing we do is we sample a particle from the previous distribution, that's from this distribution here, according to its weight. Okay, so we just sample a particle, okay? The next thing we do, this is actually a combined step, okay? It says control, but it really should say control and diffusion, right? We sample a new state using two things. Whatever the old one was, so that's the value we pulled from the particle, right? That's this xt here. We've sampled a particle. It has a particular state. That goes right in there. We also have the action. And then we have to sample from the new distribution. So let's suppose the action is take a step a meter to the right. Every time I do this, Megan goes, all right, take a step a meter to the right. And then I'm going to sample from a distribution because there's actually some uncertainty about that step, right? That's our process noise. So it's a little tight Gaussian. I generate a little bit of noise, and I add that. That's what this sampling value is here, using the previous sample, the control, and then whatever the noise is, okay? Then what I do is I re-weight that sample. What do I weight it by? I weight it by how likely would the measurement have been, this is my likelihood, okay? How likely would that measurement have been if that new sample is actually where the object was, or where the robot was? That becomes my new weight, all right? That's the multiplication step we did before. We took our prior, we had those lumps, we multiplied them, and got them through. We just keep track of the sum of those weights. We add that particle to our growing set of particles, and we do this n times. Now we're all done, except one problem. Our weights don't sum to what? They don't sum to 1, because they were whatever they were. We just did this multiplication. So all we have to do is, because we've been keeping track of the sum of the weights, that's the eta, we divide all the weights by that value. And that's normalizing the weights. When we're done, we have a new distribution, bunch of particles. Each particle is at a particular state. Each particle has a weight, and the sum of those weights is 1. And so that's a valid sampling-based representation of the probabilistic density. And that's it. That's all of particle filtering. Just stepping through this diagram, okay, we start off with some underlying distribution, pardon my inability to trace, okay, but of course we don't actually have a real distribution. What we have is a set of particles, okay? Those particles are not uniformly weighted. Remember, the sum of all the weights is 1. Some particles have more weight than others. That is, that particle has a higher probability, all right? So here's what we do. The first thing we do is we draw a set of samples from this set. Okay, now you'll notice here in this nice picture, one of my big particles happened to get sampled 3 times. The medium particles got sampled twice, and this one got sampled once. And by the way, notice, how many times did these itty-bitty particles get sampled? Not at all. That's okay, because you're doing a random sample because it corresponds to the density. And that random sampling sometimes gets all the particles, sometimes only gets the ones with significant weights. So we do the sampling. Now the next thing you'll see is that each one of these particles has been shifted, but you'll notice that the shifts are not always the same. So why do you think that is? Do you know why that is? There's a deterministic part. Nothing says that my deterministic part has to be the same for all my guesses of the previous state. Okay? Let's suppose what I do is I take a step proportional to the number of lines that are on the floor, right? So I'm going to step 3 lines. But if the lines are closer here than they were over here, relax, Megan, then going 3 lines over here would actually mean I'd moved a smaller amount than if I was over here. If I had gone 3 lines, I would have gone a further amount. All this means is that the deterministic part doesn't have to be the same everywhere. It's just deterministic. Then we add in essentially what could be thought of as the diffusion part or the uncertainty part. Remember when we were generating the new sample, we did the deterministic part plus the probabilistic part. And that's what's here, right? So after we take a sample and we move it, we add some noise, and we do that every time we had drawn a sample. So since we drew 3 samples from this particle, it ended up at 3 different places. Likewise for all the others. Then what we do is we take our measurement, and we've got P of z given x. That's what this value is. And we just multiply these weights, which are all 1 to start with, by that value. Okay? Oh, here it is, P of z given x. We just multiply it, and we end up with this new set of particles. Okay? So if I erase my figures there, you take a look. That's a beautiful figure. It's all of particle filtering. Just sleep with it under your pillow, and you'll be in great shape. So that's all there is to the algorithm that's particle filtering using sampling as a way of representing your densities. There are some details to mention about how to do that, which we'll talk about later when we do it for tracking. But before we do that, I want to show you some interesting sort of robot vision applications because they illustrate the use of particle filters really well. And then we'll revisit the pure vision tracking. But in the meantime, I'm thirsty. I'm going to go get a drink. So we'll be back for the next lesson in a bit. All right, welcome everybody. Hope you're having a great day. Back to computer vision, and we're continuing with our work in particle filters. Last time we introduced particle filtering, and we talked about the algorithm that actually implemented it. So we're using a set of particles to represent a density, and we went through the Bayes loop of essentially propagating the belief forward through both the deterministic and the non-deterministic part. Then we get a measurement, which gives us a likelihood. We multiply the prediction by that likelihood, and that gives us something using Bayes' rule that we can normalize to have a new belief, a new posterior estimate of the state. So in this lesson, we're going to look at some robot vision examples that sort of illustrate nicely sort of the simplicity of using this method. Let's take a very simple robot sensing problem, right? So let's assume that a robot knows the 3D map of its world. Okay? And for now, we're just going to worry about a robot running around on the floor, so it's not climbing stairs, etc. It's just running around. And let's assume also that it has noisy depth sensors, so it can measure depth in a lot of different directions. And they're noisy, so the measurement is uncertain, but we know about the uncertainty. That is, we have a sensor model. Okay? And it moves between frames, and it takes a set of readings, and then it moves again and takes a set of readings, and it moves again. But the idea is it keeps taking all these readings, and the question is, how well can it know its state? So what is its state? Montana? No. Its state is 3 values, x, y, and theta, its orientation. Okay? That's why we're just doing a mobile robot on the ground, 3 dimensions. All right? So just to remind you, in a Bayesian filter framework, we need 4 things. We need some sort of a prior. Remember that trip to Delphi, so you unpack your next prior. We need a dynamical system model, and that's the likelihood of landing in some new place given that you were in an old place, plus whatever action was taken. We need a sensor model. Remember, a likelihood. That's not the probability of being someplace given a measurement. The likelihood is the probability of getting the measurement given what your state was. And then we need this stream of observations and the action data, the Z's and the U's. For that robot that I described, the state is obvious, the map will be easy, etc. The thing that's tricky, not tricky, the thing we have to define is the sensor model. So here's a picture of a sensor model. And what this is this is the probability of getting a particular measurement if, let's say, the actual state was here on this black line, okay? And what was nice is when you're using a real robot, you can actually measure the likelihood. So you stick the sensor, 3 meters away, or let's see, that's centimeters, so 2.3 centimeters away from the wall. You turn it on, you collect a whole bunch of measurements, and you see what you get. That distribution would be this distribution, okay? And in fact, the blue is what was measured, right? So that's why the blue has got the noisy stuff. And the red is how they approximated it. And you can see they basically had some sort of a Gaussian function or something like that. In fact, you can see that the laser has a less noise than the sonar. Okay, so this is actually a relatively noisy laser. A modern laser would be, very precise, except that you might have some specular problems, etc. So all of that would be fine, except you'll notice there's this thing here and this thing there. And the question is, what's going on when, the thing is 2.3 meters away, and here it says 500, but the astute observer will notice you're just using the very last value. Well, what that really is that's the probability that you get no return, okay? So you're some distance from the wall, you send out your sonar chirp, or you send out your laser, and it just goes away, gets on a train, never comes back. This happens, you guys know what specular reflections are, right? So when light bounces off, etc. Turns out that sheetrock is very specular to sonar. So when you send out a sonar chirp, often it doesn't come back, it skips like it reflects off, in which case you don't ever hear the chirp come back, or it comes back after having gone through a long echo path. Likewise, if you're looking at something that's shiny, like a glass wall, when you point at it, you can see the laser beam, but when you point it on the side, okay, it'll be reflective, it'll be a specular. So what these values are is the probability of getting no return given that you're at some distance. And in fact, that probability stays the same pretty much no matter what your distance is. All right? So remember, this is not the probability that your distance is actually 500. It's the probability that you would get this no return at any given point in time. Okay? So we need to incorporate that noisy model. Here we have an example, and what the robot is actually going to do is it's going to follow this purple line. Okay? So this is where it starts, and then it goes here and it moves that way. What we're showing you to begin with is a couple things. First of all, you see all those red dots? That's its current set of particles. In other words, it has no idea where it actually is. The green is an example of where it thinks it might be. And in fact, this is the locally most likely, which is just some way of the robot guessing where it is. Now, what I'm not showing on this map is for each particle, there's also a theta, right? Particles have to represent the state. What do we say our state was? We said it was x, y, and theta. It's hard to show this in 3, so I'm only showing x and y, all right? But for any given theta that I think it is, then I would be sending out an array of sensor measurements, and I think I know where it should hit because why? Because I have a complete map, okay? So what happens is, first, your eye is just going to naturally go to the green thing. What's going on there is that's the set of sensor measurements that it's getting. So wherever it thinks it is, it puts down the measurements it actually got. Now, if it's in the right place, those measurements will actually, most of the time, hit the wall at the right distance. Every now and then it'll go right through the wall because it was a no return. All right? So let me just put it in motion. It's easier to understand. All right, so here we go. So it's a movie. So each one of these changes is when it takes a measurement, and you'll notice there's a clump of particles here. In fact, that's the most likely clump. And there's also a clump of particles there. That's a nice way of saying the robot does not know whether it's definitely here or definitely there. And the reason for that is the hallway is kind of symmetric, right? There are these doors, okay? But there's doors on both sides. So it hasn't yet been able to disambiguate, if this is the center of my universe, whether it's at this area or that area. But let me put it back in motion. What's going to happen is the robot's going to go inside in the room, and you'll notice in this room, in the room it's about to go into, there's a ottoman or whatever that is in the middle that's not in the other room. So once it goes in, yep, there it goes, okay, you'll notice the particles that are in the wrong place, they're going to disappear. Okay? Now, some of the rays are still going in the wrong direction because, they're going through the walls, but that's just the